get that all the time.
I know, it's like.
I have like 1,000.
I have 4,000. I don't know.
That's fine. I'm only here for the I do? Yeah. Sure. I don't want to be the first to go. You and I have to go. How much you have done? I finished it. I think I just finished based off the one small. Do you have like your holes? I have my holes. I have like dimensions. I just have to put holes in the small. Small little boy. Oh, I know it's like put holes in there. All right. Doing sis. Is this the answer? Okay, good. And this should be show the camera is this the answer? Rob, did you just put it up to the camera and go, is this the answer?
No, I did. I kept it on the thing.
Okay, was it good?
Recording?
Inconsiderate.
So you put the 3.6.
Is that how you should do it?
Yeah. Yeah. To make sure I think. I don't have
Oh wait, I think I'm because I'm including this.
Okay, good morning everyone. Good morning. So we'll continue with bending stress and transverse shear stress. I want to look at a problem today which incorporates all of these. Okay, we looked at the formula last time for transverse shear stress. I will use that today, and we will complete what we did last time as we solve this problem. So here is a problem. I have a cantilevered beam. And for the sake of simplicity, I'm going to assume that the cross-section of this is a rectangle. The total width of this rectangle is W. And I'm going to set up an axis system, so x-axis. Y-axis, z-axis coming out of the page. Okay, and if I look at the cross-section axis is going to be YZ. And the total thickness I'm going to say is 2t. So from the z-axis, distance is t to the top and t to the bottom. Okay? 2 times t. Then I have the length of the beam. L. And let's say that the length of the beam is 20 times the thickness of the beam. Okay, so this is 20 times t. And there are a couple of forces acting at the free end of the beam. A force of magnitude F, and and then I'm going to have another horizontal force, an axial force of magnitude. And what we want to do in this problem is the following. We want to find out what is the largest value of the bending moment, what is the largest value of the shear force, and then focusing on the cross section where this occurs, I want to look at the state of stress. Okay? So again, Vmax, based on the formula that we saw last time, which we will complete today, obtain Mmax. Then look at the cross section where this is occurring. Okay. At the cross section where Vmax and Mmax occurs, I want to look at the state of stress at a point on the top and a point on the bottom. Obtain total stress at a point on the top and the bottom. Of the cross section. Okay. So fairly standard problems, this is how we will be looking at problems from now on, is we're going to have a combination of loadings. There's going to be a force which is in essence creating a shear force. Then I'm going to have some kind of an axial force, and there will be a state of stress that will be created, which will be due to a combination of all of this. I'm going to have bending stresses, I'm going to have shear stress, and importantly, because there is a normal force acting, I'm going to have an axial stress as well. Okay, so due to all of this, we have to be treading a little carefully. So I'm choosing the simplest cross section possible to start off this kind of an analysis, and this is called as a combined loading problem. This is in 2 dimensions for the time being. We will then start looking at things in 3 dimensions. All right. First step in any of these problems is to find the support reactions. This is a fairly trivial case. I'm going to have a bending moment at the fixed end of the beam. I'm going to have an axial force equal and opposite to the force F applied. I'm going to have a reaction force which is equal and opposite to the other vertical force applied. Okay, so we're not going to spend time doing these calculations. I'm going to draw the free body diagram. Right, so there is a force F and a force F. These are wantonly chosen to be of the same magnitude so that we can come up with some conclusive answers. Total length of the beam is L. And on the fixed end of this, I'm going to have a bending moment. Okay. Or a reaction moment. So this is n suffix r. I'm going to have a reaction force which is going to be equal and opposite to the force F. I'm going to have another reaction force which will be equal and opposite to the horizontal force F that is applied. Right, so this is the reaction at the fixed end. So this is capital F as well. And this is also capital F. If I sum moments about this fixed end here, the force F which is acting horizontally will not cause a rotation about the fixed end. I'm going to have only a torque due to, or a moment due to this force F times L, which is in the same sense as what I have drawn this to be. So this is actually going to be in the opposite sense. Or if I write this out, this is just going to be minus F times L. Does this make sense to everybody? Okay, basic statics. I'm just summing moments about the fixed end. As I'm summing moments, the moment caused by this is clockwise. So this has to be counterclockwise. But I've drawn it to be clockwise, so the answer is going to be minus F times L. Okay? Shear force and bending moment diagrams. Because those are the diagrams that tell us, okay, where is the largest shear force located, where is the largest bending moment located. So I'm going to draw them next. And I want to see if there are any questions so far. Okay, we'll proceed. Shear force diagram. Bending moment diagram. So this is V, X, M, and X. And as we decided, we are not going to be doing much of a calculation when you're drawing these diagrams, okay, except for certain instances where there will be zero crossings, where you have quadratics and so on. You have one in your homework. I want you to fight with that problem because I'm going to be doing something next week which will tell you how to do it in a much more easier manner. Okay? Shear force diagram is fairly straightforward. I start off here. I have a force F that is acting, pushing me up. Nothing else going on until the end of the beam, so I just travel all the way down. And at the end of the beam, I see there is a force F which is trying to push me down, so I come back home. Okay, so this is the shear force diagram. And I start off at 0 here. Bending moment diagram. Because this is a cantilevered beam, I'm going to have a couple moment at the beginning of the beam or the fixed end of the beam. So can you tell me, if this is 0, am I going to be starting at the negative point or the positive point on the y-axis for the bending moment?
Positive. Positive.
Positive? Are you sure? See, that's the tricky thing. Look at this. Okay, so positive or negative? Another dead giveaway is that the shear force is positive. So if I start off positive, I'm just going to keep climbing positive. You don't want that to happen, right? So you're going to come back to 0. But the right way to look at it is the following. So this is drawn clockwise. This is drawn clockwise, but it has a negative value. If I have a clockwise couple moment, it causes an upward jump in the bending moment diagram. But because its value is negative, I'm going to start as minus F times F. Okay, so I'm starting here. Minus F times L. At the end of the beam, I'm going to take this minus F times L and add it with the area under the shear force diagram, which is the total length is L. So F times L minus F times L is 0. And how do I go from the beginning to the end? The slope of the bending moment diagram is the shear force value. The shear force value is constant, which means the slope is constant and positive because the shear force value is positive. So I'm going to go along a linear path all the way to 0. So this is the bending moment diagram. So this is linear. We'll start solving more complicated problems as time goes on. Okay. So bear with me as we get through the basics. Then I look at the question. The question is asking me, okay, at the cross section where the maximum shear force and the maximum bending moment occurs, start looking at the stresses. So my question to you, first things first, okay, it is not necessary that the location of the maximum shear force is also the location of the maximum bending moment, as you have clearly seen in your shear force diagrams and bending moment diagrams in your homework. This is a special problem because the shear force is constant all through the beam, which means that whatever cross section I slice through this beam, the shear force is going to be of the same value as capital F. If I look at the bending moment is decreasing or negatively increasing from a large negative value to a small negative value, negatively decreasing, I'm sorry, or increasing in some sense. So this is increasing or negatively decreasing. So which means that the cross section where the maximum shear force occurs and the maximum bending moment occurs is going to be right at the fixed end. Does this make sense to everybody? Okay, so V max is capital F. M max, look at this, I'm not changing the signs here, I'm not messing with the signs. M max is minus F times L. Or I can say that it's plus F times L, but in the opposite sense. So watch what I'm going to do next. I'm going to set up a view. So this occurs, first of all, occurs at the fixed end. Okay. So I'm going to set up a viewpoint. I'm going to have my axis system, x-axis, y-axis, z-axis. This is the x-axis, the y-axis is the vertical axis, z-axis comes out of the page. And I'm going to take this beam, tilt it towards you, and draw its three-dimensional view from the perspective of the person looking at this beam, staring straight across its face. Okay, so if I do that, I end up with the following figure. And I'm going to keep that figure for the rest of the problem because we're going to deal with that in some sense. So this is the view at the fixed end. Okay, so this is the cross section that you're visualizing. I'm going to draw the axes. As you can imagine, the cross-sectional axes will be the y and the z axis. Centroid. Centroid is easy to find in a rectangular cross section, so this is right at the geometric center. This is the z axis. The x axis is into the page. This is the x axis. Important thing to recognize, what is the axis where the bending moment is acting? Is it the x-axis, the y-axis, or the z-axis? The z-axis, right? So in this problem, the bending axis corresponds to the neutral axis. That's always the case. If I have an axis of bending, for that particular bending stress calculation, that corresponds as the neutral axis. Okay, so I'm going to draw the bending moment. Watch this very carefully. It is drawn as clockwise, which means that if I'm using the right hand rule, if this is a z direction, forget the fact that it's minus f times L. This is the z direction. Right hand rule says that the moment has to be pointing along the negative z direction. I'm going to draw it exactly that way. But I'm going to say that this is minus f times L. And this is actually M max. And so my z-axis is a neutral axis. This is the centroid. What other forces do I have? I'm going to have a shear force which is pointing vertically up. So I'm just going to draw it here. this is my shear force. Any other force that I see on the cross section? I see a normal force that is coming out of the face. Don't forget that, because normal forces, they cause an average normal stress. I'm going to have bending stress, bending moments which cause bending stress. They have either an additive or a dilatory effect on each other. Okay? So I'm going to have a normal force, N, which is coming out of the board. Okay? And so these are all the forces and the moments that I have on the cross section. So these kinds of figures are a must, which is why I don't want to have these on the current midterm exam and so on. You figure out what the support reactions are, draw the shear force bending moment. This problem alone might take an hour in a final exam, okay, because you're going to do this in 3 dimensions. Okay, but this is how reality is. If you're looking at a pipe that is bending and you want to understand what are the stresses that cause it to break, this is exactly what you're going to be doing. You're going to be drawing out the shear force bending moment diagrams based on the loads applied, figure out which cross section of the pipe is the weakest, and then find out, okay, due to which kind of effects is the pipe breaking? Is it because of bending stresses, or is it because of normal, average normal stresses, or is it because of shear stresses, or a combination of all of these? Okay, that's our main aim eventually. So you draw the shear force bending moment diagrams, figure out where the cross section contains a maximum of these, draw out a 3-dimensional viewpoint, mark all the forces, then go on our merry journey. Okay? I write down some geometric details. So this is T. This is also T. The total width is W. And the moment of inertia calculation about the neutral axis. So INA is 112 base times height cube. What is the base? The base is the width W here. The height is 2 times T. So this is going to be 112 W 2T cube. 2 cube is 8. 8 by 12 is 2 by 3. Okay, so I neutral axis is 2 by 3 W T cube. Okay, so that's one thing that we mark out here. And I'm going to keep this figure for the rest of the class, lecture. This is the maximum bending moment. I have not changed its sign. Please notice that. Normal force, then a shear force. And one more thing that I want to write down is the area of cross section, which is fairly a silly thing. It's a rectangle, so base times height. So area, base times height is 2 feet. And the last thing I want to point out before we move on to calculating stresses and so on is, in the problem, the length L is given to me as 10 times the thickness. Okay, this is 20 times the thickness, I'm sorry. So 20 times T. L is 20 T. Okay, any questions so far? I'll give a brief pause so that you catch it. Free body diagram, shear force bending moment curves, cross section where the action is taking place, based upon the viewpoint that I've set up. It is very important that you set up an axis system first, coordinate system, and you stick to that coordinate system throughout the length of the problem. Because we're going to start looking at these and writing out what is called as a stress matrix, which is a collection of all the stresses that are acting on this body. I'm going to take off this particular panel here. Okay. All right, now took off the panel there, but the panel said that I am interested in finding the total state of stress at a point on the top and the bottom of the cross section where the maximum things are occurring. So I'm just going to call that point this point A, some point here. Okay, so some point A, then some other point B. Okay, so these are the points that I'm interested in. First things first is we will start off by looking at the easiest of the lot. The easiest of the lot is the effect of the normal force. What's the normal force trying to do? The normal force is trying to take all of the particles. If you think of the cross section as a collection of particles, it's going to take all of these particles and based on its direction, pull them out. And that's going to cause an average normal stress. Okay? So effect of the normal force. I'm going to draw the cross section very simply. What's the normal force trying to do? It is going to cause an average normal stress. So sigma average, which we know simply is a normal force divided by the area of cross section. The normal force is equal to little f for us. Okay, so that's something I'm going to label here. Does that make sense to everybody? This force F is the normal force at the cross section, so this is equal to N. And so I'm going to call this area as 2 times Wt. The normal force N is capital F, so this is F by 2 Wt. Is it tensile or compressive?
Tensile.
Has to be tensile, right? Because the normal force is positive. According to the sign convention, it is pulling all these fibers out. So this is a tensile. Stress. We don't need to show this. This is just for our own understanding. I am not expecting to be drawing all of these things on every problem. But if I draw the total normal stress field, a field is nothing but a collection of all the stress arrows. Okay, so it's going to look like this. Each and every point on the cross section is going to be subjected to the same normal force, which is going to be sigma average, which is N divided by A. So this is sigma average. I'm going to set up a directionality for this. Centroid, y-axis, the z-axis or the neutral axis. So what is the direction of the normal stress? The normal stress is going to be acting in the direction perpendicular to the cross section. So this is going to be sigma x. But we said last time that every normal stress is going to be labeled as sigma II. Okay, watch this. Can everybody see my writing? People in the back? Okay. Sides too, right? This I, the first index is the direction of the stress. The second index is the direction of the area. In this particular problem, this is fairly straightforward because my x-axis is perpendicular to the area of cross-section I'm looking at. So this is x-axis. So the second index is I. The direction of the normal stress is also in the x direction. So this is going to be called a sigma average xx. And this is equal to F by 2W.